So we've all gone hiking, whether it is in parks, mountains, canyons, wherever it is. But those of us who don't have previous problems going to high elevations rarely consider altitude sickness when they're enjoying the scenery thousands of feet above sea level. So for most of us, that's fine, and we never get altitude sickness or feel sick in our whole life. Um, but for some of us, it's a serious thing, one that could cost them their life. So even those in excellent shape can get altitude sickness, which can be possibly made worse by fatigue. And an extreme example is the death zone of Mount Everest, which some of you may be familiar of, where the tallest peak in the world is 29,000 feet above sea level. And there's so little oxygen that the body starts to die minute by minute, cell by cell. So heart attack, stroke, altitude sickness can all occur at that altitude. But how can we try to prevent this through a simple and efficient way that can detect your altitude sickness risk as you ascend a mountain? So in this project, we'll be using two different methods, oxygen percent and heart rate, in order to address the altitude sickness. So I'm not a doctor, and the objective of this project isn't to understand the altitude sickness process in detail, and we can't tell you how quickly you'll get altitude sickness with this certain condition. But what we are going to do is try to devise a method on how to monitor your altitude sickness risk when you're hiking up mountains. So one thing to keep in mind is that everything is relative, and even the test subjects that we use exhibit different oxygen percent decreases and heart rate increases for different altitudes and levels of fatigue. So everything is different, and some people, again, might not ever get altitude sickness. Nevertheless, based on this project, we can give you a rough estimate from our experiment on what oxygen level and what heart rate to start being alert of the altitude you're reaching and focus on managing the risk of altitude sickness before you might get it. So here is a 3x3 table that is designed to help you understand our hypotheses. So there's two variables that we'll be changing in our experiment, one factor at a time. That is fatigue, and so intense exercise versus moderate exercise for fatigue, and altitude level. So the response variables are oxygen percent and heart rate, and these are the hypotheses that we'll be expecting and testing. So first is altitude level and oxygen percent, as you can see on this part. And we expect a negative correlation between oxygen percent and altitude level because the higher up in the air you are, the less oxygen there is, and thus your body will receive less oxygen and have a lower oxygen percent. So next is heart rate and altitude level. So we don't think there's going to be a negative or positive correlation between the two because we're not sure how heart rate changes with altitude level based on our scientific research, which I'll talk about next. And then for oxygen percent and heart rate, so that's a tricky one. And to describe this, there's many different layers. So in higher altitude, we'd expect less oxygen percent in your blood. So this is what we got from the previous slide. And we think that less oxygen percent in humans' blood can cause them to fatigue faster. And this greater fatigue level is detected or can be detected by higher heart rate. So we do expect oxygen percent and heart rate to be negatively correlated since less oxygen percent and a higher heart rate, but this is not like a causal relationship as less oxygen percent in blood causes more fatigue, which causes higher heart rate. So it's not directly less oxygen percent directly causes more fatigue. So the two causal relationships are listed in the following two bullet points. So we expect higher altitude to cause less oxygen percent in blood and more fatigue to cause a higher heart rate. So before we conduct any statistical tests or gather any data, let's understand the science behind altitude sickness and what exactly is altitude sickness. So at higher altitude, the pressure drops and less oxygen is available, as you can see in this chart. So anytime you're above 8,000 feet, your oxygen level can be below 80%, and you can be at risk for altitude sickness. And this chart shows the oxygen levels at different altitudes, and you can see that oxygen level decreases as altitude increases. So there are three kinds of altitude sickness, each with varying intensities. So the first type is acute mountain sickness, and that's the mildest form of altitude sickness and is quite common. Dizziness, headaches, shortness of breath, muscle aches, nausea can all be symptoms of AMS. And the more severe and second type of altitude sickness is high altitude pulmonary edema. So this occurs when there is buildup of fluids in your lungs, which is your body responding to the high elevation and a lack of oxygen. Dyspnea is also common when you have acute shortness of breath, whether when you're walking and exercising or when you're doing non-strenuous activities. So more advanced symptoms like gurgling in chest and a pink frothy sputum is, which is when you cough up blood, is when you need to seek immediate help. And the last and most severe case is the high altitude cerebral edema. And you might have noticed it's cerebral, which means relating to the brain instead of pulmonary of the previous disease, which is relating to the lungs. So it starts off as severe headache, drowsiness, vomiting, and ultimately coma, and when left untreated is death. So from all this, what we know is we want to prevent the two latter altitude sicknesses, so the high altitude cerebral edema and high altitude pulmonary edema. So we want to detect altitude sickness in the first phase of acute mountain sickness before it transitions to the more severe one. So that's what this project is going to aim to do and focus on prevention techniques. So speaking about prevention techniques, let's see some recommended guidelines to prevent altitude sickness. So chances of altitude sickness depends on how quickly you move to higher elevations, how high you move, the altitude of where you sleep as your body grows more accustomed to the elevation when you sleep where you live. The higher elevation you live, the less likely you're going to develop altitude sickness since you're more used to higher altitudes. And also you just wanted to include that it is independent of age. So yes, your medical history like asthma, if you've experienced altitude sickness before, stuff like that. Those are going to alter your chances, but it is independent of age, and many studies show basically no correlation between age and altitude sickness. So it is recommended that you start your journey under 10,000 feet to drink 3 to 4 quarts of water daily and don't use tobaccos, alcohol, other medications, stuff like that. So these are all possible to do, but most people don't really go up an additional 1,000 feet every day. So that's kind of a lot to ask, especially if you're going up a mountain. So we actually did this project in Rocky Mountains, and the visitor center was at the 8,000 feet mark, and only takes an hour or two to reach the highest elevation possible by car, which is 13,000 feet. So if you're going to follow this guideline, then that means you take like 5 hours, which is quite a long time. So most people just directly go up there. So altitude sickness can still be quite likely, especially considering that a lot of people don't follow some of the guidelines. So the tool we use to measure oxygen percent and heart rate is the pulse oximeter. So this can measure both heart rate and oxygen percent simultaneously. So not only does it save money, so you don't have to buy 2 separate devices to measure oxygen percent and heart rate by itself. Also, we won't have a time difference problem if we choose to measure oxygen percent first and then heart rate next, or vice versa. So the pulse oximeter is recommended by doctors to use, so it's quite a safe choice. And so to use the pulse oximeter, just slip it on your finger and press the button here and wait a second or two, and the oxygen level and heart rate appears on the monitor. So we also ensured the measurement is reliable and repeatable, since we have, a lot of people. We have more than one test subject, by measuring the oxygen level multiple times afterwards for each person. Okay, so we've collected the oxygen and heart rate at sea level in San Jose, California, roughly, which is roughly sea level just 87 feet above sea level. So it approximately works, and 5,000 feet above sea level in Boulder, Colorado, 8,000 feet in Rocky Mountains National Park in one of the visitor centers, and again at the 12,000 feet in Alpine Visitor Center. So to measure the fatigue factor, we incorporated a 150-second jump rope session at the 12,000 feet mark. And the reason why we chose that duration is because a lot of our test subjects started feeling tired at that time interval, which is quite surprising because the people we tested were young people and children. So them being fatigued after just 2.5 minutes of jump rope comes to show that altitude level does affect fatigue. So the oxygen percent and heart rate actually did not change within 1% for oxygen and 2 for heart rate beats per minute between the sea level measurement all the way up to the 8,000 feet mark. So basically didn't change. So the data that we'll be comparing in our statistical analysis is the 8,000 feet, 12,000 feet, and the 12,000 feet with the fatigue factor, which is the 150-second jump rope. So the last 3 bullet points. So we only have 5 people sample, and they're all ages 13 to 17, so a fit and young group. So we actually did this when we were going to a conference. So yeah, we weren't really wasting any time. But as you can see, the sea level and oxygen percent basically didn't change for 8,000 feet and started to drop in the 12,000 feet and continued dropping after the oxygen percent, after the fatigue factor. So the heart rate is listed on the right, and you can see that it gradually increased from 8,000 to 12,000, and then increased quite a lot to the 12,000 with fatigue. So as you may recall, 8,000 is when the altitude sickness can start occurring. So we did test the elevations that can cause altitude sickness, starting from the 8,000, which is a good elevation to start measuring the risk. So first, before conducting any hypothesis testing, we tried to understand how these different variables are related. So on the left side is the color map on the correlations between the 6 variables. The 6 variables being oxygen percent at 8,000, 12,000, and 12,000 with fatigue, and then heart rate at 8,000, 12,000, and 12,000 with fatigue. So you can kind of see the clusters in the color map. One in the top left-hand corner with high correlation, the redder, the more correlation, the bluer, the less correlation, or the bluer, the negative correlation, and then the gray is random correlation. And you can also see more correlation at the bottom right-hand corner. So these are the 2 clusters, and the first cluster is composed mostly of oxygen percent, and the second is composed mostly of heart rate. So this may indicate that these 2 methods, oxygen percent and heart rate, don't show and represent the exact same thing. So this could be because oxygen percent is more related to altitude and heart rate is more related to fatigue. So next we conducted the two-way hierarchical clustering on the 5 different test subjects, which you can see on the heat map shown here. This just shows that everyone has different oxygen heart rate behavior. So subject 1 and 2, you can see the subject labeled on the left. Subject 1 and 2 seem to have similar patterns across the 6 variables, as indicated by mostly, they have similar parts where they're highly correlated and not as correlated, and they're actually the first cluster they're the first test subjects to be joined in the cluster. So test subject 4 has a blue square for almost all of the variables, and thus has negative correlation with the others. So the scree plot on the bottom also shows us how many clusters we should choose. So since we only have 5 test subjects, the smaller the number of the clusters, the better. The scree plot seems to indicate that 2 clusters is a good number, although it's not extremely clear, as it has quite like a linear segmented pattern due to a small sample size. So it's not the ideal elbow pattern, but it can still help us divide the clusters, and it seems that 2 is the ideal cluster. So we can also use the parallel plot to visualize the patterns and how the 6 variables differ. So you can see that for oxygen percent, the 4th test subject, relatively lower which may indicate that they have higher risk of altitude sickness because they have less oxygen percent than the others. But for heart rate, they're also on the lower side. So test subject 4 is quite hard to predict, as we kind of expect lower oxygen percent to have higher heart rate, but which is exemplified by everybody else except for test subject number 4. So this just shows, again, that everyone's oxygen levels and heart rate changes differently across the different elevations and fatigue factor. So everyone has a different behavior. And athletes who climb frequently can use these methods to study their limitations and how their body responds to changing elevations, and discuss this, with their doctor or medical professionals. So now that we understand the patterns of how the variables interact and differ by person, we want to conduct hypothesis tests to have a more quantitative estimate of how much this conforms to our hypothesis. So we want to know if we're 95% confident that oxygen level does decrease with increasing elevation and heart rate does increase with greater fatigue. So we also want to see if there are any underlying patterns that we didn't expect, such as a possible cross-correlation between oxygen level and fatigue, and heart rate and elevation. So we'll be using the pair T test since everyone's behavior is different. And we're interested in the mean difference to compare the before and after state specific to each person. So we're going to be using the pair T test, not the two sample T test for that reason. And another reason is also because everyone's behavior is different. And we want to check normality first before we use the parametric pair T test. And looking at the box plot, there doesn't seem to be any obvious skew or outliers, and they all seem pretty normal. Interestingly, for oxygen percent, the standard deviation increases with higher altitude and greater fatigue. The reason why the oxygen percent starts similar is because we used a cluster sampling for only teenagers. So everyone exhibits different behaviors, so the range in standard deviation increases with increasing elevation. So the standard deviation for heart rate, however, doesn't seem to change too systematically. Okay, so here is the pair T test for oxygen percent for both altitude and fatigue. And the right-hand side compares the mean difference for oxygen percent across 8,000 and 12,000 feet. And the p-value is less than 0.05. So the diamond graph here also indicates that this, the horizontal line here is below 0, and the 95% confidence interval bands, which is the dotted lines, also does not cover 0 like expected in a hypothesis. So this can be strong evidence that at greater altitudes, there is a higher chance of altitude sickness due to lower oxygen levels. So also the oxygen percent difference is also significant for fatigue, which we didn't expect initially. This may be because, when you're more fatigued, you might lose oxygen more easily, which can cause even lower oxygen levels. But that's just a possible explanation, and further research and experimentation would be needed, as we were only hypothesized the altitude sickness and oxygen percent. So next is the pair T test for heart rate for both altitude sickness and fatigue. So the right-hand side compares the mean difference for heart rate across 8,000 and 12,000 feet. And the p-value is less than 0.05, but less significant. So it's not highly statistically significant, which is less than 0.01. So oxygen percent is more significant than heart rate for altitude elevation differences, which is expected. So why heart rate and altitude sickness are related. Further research might help explain why that would occur. But heart rate is also significantly different for 12,000 feet with fatigue versus 12,000 feet without, as expected. And it is statistically highly significant, p-value less than 0.01. And fatigue and heart rate is also more statistically significant than altitude sickness. So yes, both mean differences are statistically significant, but the practical difference is a heart rate of 74 for heart rate in fatigue than heart rate in altitude sickness of only 11.8. So practically significant the fatigue has a greater difference than altitude sickness. So in conclusion, we're able to study the altitude sickness types and prevention techniques, as well as use the oximeter to measure oxygen percent and heart rate across different elevations. So we conducted multivariate clustering, two-way hierarchical clustering, and parallel plots to study the patterns between different variables in test subjects. Lastly, we used the paired t-test to compare heart rate and oxygen percent between 8,000 and 12,000 feet, in addition to 12,000 feet and 12,000 feet with fatigue. So their heart rate is higher and oxygen percent is lower at higher altitudes and greater fatigue. So why oxygen percent fatigue might be related and why heart rate and altitude might be related is less obvious, and further research can help clarify their patterns. So also this test can also be applied to more people to ensure a more representative sample by sampling more people across different ages and different backgrounds. So yeah, that's all I have for today. Thanks for listening, and I'm open to any questions that you might have.